Okay, asymptotes and end behavior. So in the last example, I walked through a case where there was breaks in my function. We talked about what happened at the breaks. And then we talked about the end behavior, what happened at the tails of my graph, right? End behavior, we talked about end behavior polynomials. And polynomials will shoot off to positive or negative infinity depending on whether they're even or odd. With rational functions, the end behavior will approach certain things, and we'll get into that. So asymptotes and end behavior. So first, vertical. So there's different types of asymptotes and different types of end behavior, and we'll get into those. First, vertical asymptotes. So I'm going to look at the simplest rational function. So the simplest rational function is 1 divided by x, where 1 is a constant function, constant polynomial, and x is a simple linear equation, y equals x. All right, the domain of this, excuse me, is everything but 0, right? I can't divide by 0. So the domain, always understand what the domain is. X cannot be 0. So negative infinity, and there's a break at 0. Always important to remember what the domain is, because that's where the interesting things happen. Interesting thing happened, that value is not in the domain. And so 0 is not in the domain. And so what happens near 0? Well, as x goes to 0, as my x values approach 0, what happens is the y values approach, and I did the absolute value because they approach infinity. So they can approach either positive or negative depending on which side I'm on. So sometimes they both go to the same direction. Sometimes one side goes to positive infinity, one side goes to negative infinity. But either way, whenever there's a break in this case, whenever there's an asymptotic behavior, it approaches infinity, either a positive or negative infinity to the left and the right. Right? If we graph it, we'll see that. So then the graph of 1 over x. Right? If you graph this function, so there's my x-axis, y-axis. And so it comes up and approaches it like this. And so again, this would be the x equals 0. That's what the y-axis is. To the right, it's shooting off to positive infinity. To the left, it's shooting off to negative infinity. So it is. As my x values approach 0, right, 0 is the one in the middle. As the x values get closer and closer to 0, the right side of that 0 goes off to infinity. The left side goes to infinity. So again, as x goes to 0, my y values shoot off to infinity. Absolute value means one side goes to positive, one side goes to negative. Alright, so we're going to extend this idea to all rational functions. Alright, so by definition, if my function r of x is a rational, meaning I have two polynomials divided together, if the value k, so there's some constant not in the domain of the function, and this is a very important and. Alright, so because there's two things that can happen when you don't have a value in my function. Not only does the value have to cause me to divide by 0, so k is not in the domain, but you have to have that infinity behavior. As my x values get closer and closer to, that should be a k, not a c, closer and closer to k, then my function values approach infinity, either positive or negative. So I use absolute value, so it's either shooting off to positive or negative, and so that has to be a vertical asymptote. Right, so it causes division by 0. And the behavior of the graph is one side shoots off to, so as I get closer and closer to it, I'll have a side that shoots off to infinity or negative infinity. So again, line x equals k is a vertical asymptote of the graph of f of x if my function shoots off to negative infinity or positive infinity as x approaches k from either the left or the right. Alright, so finding them. So finding vertical asymptotes or holes in the function. So there's two things that can happen when we get division by 0. Alright, so again, I get division by, so that's the first thing. The domain is everything but what causes me to divide by 0. Alright, so only current values not in the domain. So again, those are the values that can cause division by 0. And so in algebra, what we do when we find vertical asymptotes of rational functions, first thing again, you should know the domain because again, what causes me to divide by 0. And then we reduce the rational expression. So I mean, what we do is we look to see if there's any common factors that can reduce to 1. Common factors are not asymptotes. What they are a hole in my function, which are still important. And when we go to graph it, we want to graph those points as open points on my graph. There's a break there, but it doesn't have asymptotic behavior. There's a break, there's an open point, but to the left and the right I'm not shooting off to infinity, ergo not an asymptote. Alright, so there's a hole in the function. If, once you've reduced, you still have a factor, x minus a, in the denominator, so you still have something that's going to cause me to divide by 0 in the denominator, then that something is a vertical asymptote. And if you look at the graph of the function, to the left and the right of it, I should be shooting off to an infinity. Alright, so that's the asymptotic case. So the second case where you get a hole in the function, if, like I said, if you've got a common factor, so x minus b is in both the numerator and the denominator, they get canceled out during the reduction. They get reduced. The graph of the function has a hole in it at that point. Not an asymptote. All right, and again, you can find the hole by using the reduced fraction. Again, it is not an asymptote. So there are two things that can happen for values not in the domain. All right, so A is not in the domain and B is not in the domain. A gave me asymptotic behavior because it's division I couldn't get rid of. B doesn't have asymptotic behavior because it was a common factor in both the numerator and the denominator and I could reduce it. And because of that, I don't have asymptotic behavior, but I do have other important behavior. The other important behavior is that I have a hole in my function, and that's still important. It's important that when I go to graph it, I indicate there's a broken moment here, but that's it. There's just a broken open circle dot at that moment. All right, and we're going to practice that in the next set. So what are asymptotes and holes in the function? And now we're going to practice it in the next video.